So in this video, I would like to explain worksheet questions of states of matter. In states of matter, we are dealing with gases and liquids. So here I have selected some important models. We'll discuss one by one. First question. So 1 liter closed flask contains a mixture of 4 grams of methane and 4.4 grams of carbon dioxide. The pressure at 27 degrees centigrade is. Direct question. So here given number of moles of CH4. Number of moles means we know given weight by gram molecular weight, that is 4 by 16, 0.25. Similarly, number of moles of CO2, given weight 4.4 by 44, which is 0.1. Therefore, total number of moles N total equal to 0.25 plus 0.1, which is 0.35 total number of moles. So from this, pressure will be equal to nRT by V. So here N is number of moles 0.35 and R value universal gas constant 0.0821 into temperature 27 degrees centigrade, convert it into kelvins 300 by volume 1 is given. So therefore pressure will be equal to 8.6 atmospheres. So option will be A. Next. So which are the following gases has maximum van der Waals constant A? So van der Waals constant A, very important. Van der Waals constant A directly proportional to force of attraction between gas molecules. So as the force of attraction between gas molecules increases, A value increases. So again, force of attraction depends on polar nature. In given options, NH3 is polar molecule. So therefore, between NH3 molecules, there will be force of attraction. So A will be more for NH3 due to polar nature. So as the polar nature increases, force of attraction increases. Therefore, A value also increases. A value is highest for NH3 due to its polar nature. So option will be D. Next. So this is also very important. Compressibility factor Z is lower for NH3 and CO2 gases than N2 gas because of. So compressibility factor equal to PV by nRT for N moles. N moles of gas, which is equal to PV by RT for 1 mole. Next. Here for NH3 and CO2, A will be more. So attractive forces will be dominating in case of NH3 and CO2. So due to polar nature. Next. For N2, which is completely non-polar, there will be no charges. A will be very less. So therefore, as the value of A increases, compressibility factor increases. One second. So as the value of A increases, compressibility factor decreases. So therefore, compressibility factor is lower for NH3CO2 than N2 gas. So due to attractive forces. A will be more means attractive forces. So among NH3CO2 and N2, attractive forces are dominating for NH3 and CO2. So therefore compressibility factor decreases. So compressibility factor decreases means Z less than 1. So option A. So as the force of attraction increases, A value increases. So as the value of A increases, compressibility factor decreases according to the relation Z equal to 1 minus A by VRT. Take this relation. So as the value of A increases, Z decreases. So compressibility factor for Z is lower for NH3 and CO2 when compared to N2. So due to increase of attractive forces, that means increase of A value. So option A. Next question. The average molecular weight of air which contains 21% of O2 and 79% of N2 is. So average molecular weight equal to percentage of oxygen into 21 into its molecular weight, which is 32, plus percentage of nitrogen into its molecular weight by total 100. So therefore it will be equal to 28.8. So average molecular weight of air is 28.8, which contains 21% of O2 and 79% of N2. So option D. Next. So gases deviate from ideal behavior at high pressure because the gas molecules. So first I will write ideal conditions. Ideal conditions are very low pressure and very high temperature. Real conditions are high pressure and low temperature. Remember these conditions. So why gas is deviating from ideal behavior means due to, that means at high pressure, attractive forces increases between gas molecules. Attractive forces increases. So between gas molecules. Therefore, they will be deviating. Ideal conditions means here no interactions. Here no interactions between gas molecules. But at high pressure there will be attractive forces. So therefore, due to this reason, gas is deviating from ideal behavior. Option A. So no interactions means here attractive forces, repulsive forces will not be there at ideal conditions. But at high pressure, attractive forces between gas molecules will increase. Therefore, deviation will be more. Next. So which gas has a density of 1.24 grams per liter at 0 degree centigrade and 1 atmosphere pressure? So we know density equal to Pm by RT. Ideal gas equation in terms of density. So density is given 1.24 and pressure 1 atmosphere. We can calculate molecular weight by R value 0.0821 into temperature 0 degree centigrade 273 in kelvins. Therefore, let M value as 28. So here 28 is molecular weight of CO. See 12 plus 16, 28. Therefore, density of 1.24 grams per liter is valid for CO. Option C. Next. The most probable velocity of a gas at 70 to 100 is equal to RMS velocity of helium at 27 degrees centigrade. The gas is. So here most probable velocity of a gas equal to RMS velocity of helium. So here at temperature 70 to 100 kelvins and here temperature at 27 degrees centigrade, that is 300. Let 300 here. 300 kelvins. Next here most probable velocity 2RT by M. T1 M1 since R is constant and root RMS velocity 3RT by M T2 M2. So from this root value cancels. So 2 into temperature 70 to 100 by, take this as M1. Next here 3 into 300 by M2. Molecular weight of helium is 4. So from this M1 value is 64. So here 64 is molecular weight of SO2. Therefore, the gas is SO2, option D. Next. Among the following graphs correctly represents Boyle's law. So we know Boyle's law at constant temperature and number of moles of gas, volume of a given mass of gas inversely proportional to its pressure, or we can write PV equal to constant, or P1 V1 equal to P2 V2. So here P1 V1 are initial conditions and P2 V2 are final conditions. So relation between volume and pressure is inversely proportional. If volume increases, pressure decreases. Therefore, clearly graph C. So here graph C is rectangular hyperbola. Graph is rectangular hyperbola. Very, very important. If volume increases, pressure decreases. Option C. Next. So very, very important question. Here root mean square velocity, RMS velocity of O2 is given 500 meters per second. Next. Temperature is constant here. Calculate RMS speed of H2 at the same temperature. So first for right, RMS speed of H2 will be equal to root of 3RT by molecular weight of H2 and RMS velocity of O2 root 3RT by molecular weight of O2. So therefore URMS H2 by URMS O2 will be equal to root of molecular weight of O2 by molecular weight of H2. So therefore URMS for H2 equal to, so molecular weight of O2 32 by 2 under root URMS of O2. So this value will be given by 32 by 2, 16, root 16, 4 into RMS speed of O2 is 500. That is total 2000 meters per second. This is the value. So option B. Important and simple question. Next question. 1 mole of an ideal gas occupies 12 liters at 297 degrees centigrade. What is the pressure of the gas? This is also simple. So here given volume equal to 12 liters. Next, number of moles 1 mole. Next, temperature 297 plus 273 in kelvins, which is 570 kelvins. Next, R value 0.0821 liter atmosphere mole inverse Kelvin inverse. So from this we can calculate pressure P equal to N naught T by V from ideal gas equation. So here N is 1, R value 0.0821 to temperature 570 by volume 12. We'll get value as 38.99 atmospheres. So here we have to convert atmospheres into kilopascals or pascals. So we know 1 atmosphere equal to 1.01325 bar or 1.01325 into 10 power 5 pascals or Newton per meter square. You can write. So 1 pascal equal to 1 Newton per meter square. So from this we can write 101,325 pascals. So therefore pressure equal to 38.99 atmospheres, which is equal to, you can convert 38.99 atmospheres into pascals. We'll get value as 395 kilopascals. This is the answer. So option B. First atmospheres, next atmosphere to kilopascals. So change here option C as only pascals. Therefore, option B, kilopascals. Nitrogen gas pressure inside a container of volume 2.6 centimeter cube or ml is 2.3 atmospheres at 27. The approximate number of moles of nitrogen present in the container. R value is given. So simple one. So pressure is given 2.3 atmospheres and volume 2.6 centimeter cube or 2.6 ml or 2.6 into 10 power minus 3 liters. Temperature 27 plus 273 300 kelvins. So R value is given. We can calculate number of moles N equal to PV by RT. So pressure is 2.3 atmospheres. So volume 2.6 into 10 power minus 3 liters by R value 0.0821 into temperature 300. We'll get number of moles as 2 into 10 power minus 4 moles. Moles of N2 present in the container. 2 into 10 power minus 4 moles. So option D. Next. So what is the approximate most probable velocity of oxygen? The kinetic energy of 1 mole of oxygen is given. Simply here kinetic energy equal to 3 by 2 nRT for n moles. That is equal to 3 by 2 RT for 1 mole. 1 mole of O2 gas. So therefore Ke equal to simply 3 by 2 RT. That implies RT equal to 2 Ke by 3. Next, Ke value is given, which is 3741.3 joules. Next, most probable velocity UMP equal to root 2RT by M. That means 2 by M into, in place of RT we can write 2 Ke by 3. So substitute the values. 2 by, so molecular weight of oxygen 32, 2 into, what is Ke? 3741.3 divided by 3. Next. So here 32 will be in grams. We can convert 32 grams into kg. Therefore it becomes 10 cube in SI units. Therefore most probable velocity is, we'll get root over 155,887 joules per kg. Therefore, option C is correct. Or here we can write most probable velocity in meters per second. Here we can write root over 155,887 meters per second. So option C. Next. Graham's law question. Rate of diffusion. Rate of diffusion of SO2 versus rate of diffusion of a given gas equal to volume of SO2 into T of gas by volume of gas into T of SO2, that is equal to root over molecular weight of gas by molecular weight of SO2. Substitute the values. Here volume of SO2 12 into time must be in seconds, 300 seconds, 5 minutes is given. Next, volume of gas 120 into 1 minute is given, 60. That is equal to root over molecular weight of gas, say m, by 64. So therefore m value will be 16. Therefore option D, 16 value. Next, the 96 grams of O2 and 56 grams of N2 are mixed to develop a pressure of 10 atmospheres, which is total pressure. Next, we have to calculate partial pressure of oxygen in atmospheres. So first I will write given values. So weight of O2 96 grams, molecular weight of O2 32 grams, say it is gram molecular weight. Next, weight of N2 56 grams, molecular weight of N2 28 grams, gram molecular weight. Next, total pressure. Ten atm atmospheres. So therefore, partial pressure of O2 equal to mole fraction of O2 into P total. So mole fraction of O2 means number of moles of O2 by number of moles of O2 plus number of moles of N2 into P total. Therefore, partial pressure of O2 equal to number of moles of O2 means again weight by molecular weight. So what is weight? 96 by 32 divided by 96 by 32 plus 56 by 28 into P total is 10. So which is 6 atmospheres. Answer will be 6. Next question. The kinetic energy in joules of CH4 at temperature T is X, then kinetic energy in joules of O2 at the same temperature is. Next, at constant temperature, at constant temperature, Ke will be constant. Therefore, kinetic energy of CH4 is given as X joules. Therefore, kinetic energy of O2 will be same. That is constant. Since temperature is constant, kinetic energy of CH4 and O2 will be constant. Therefore, option A. Next. Two flasks A and B have equal volumes. A is kept at 300 kelvins having H2 gas and B has same mass of N2 kept at 600 kelvins. Ratio of kinetic energy of gases. Kinetic energy ratio. Suppose first Ke1. We know 3 by 2 nRT. So same amount means say W is the weight. W by 2. This is for hydrogen. For H2 gas Ke1. N into R into T. 300. Next Ke2, which is for N2. Ke2 equal to again 3 by 2 into same weight W by 28 into R into 600. Therefore, Ke1 by Ke2 equal to 3 by 2, 3 by 2 cancel. So W by 2 into 28 by W into 300 by 600. So 7 is to 1. Therefore, Ke1 is to Ke2 equal to 7 is to 1. This is the ratio. Or answer 7. Next. So what is the density of 1 mole of helium? Molecular mass we know 4 at 300 kelvins and pressure of 0.82 atmospheres. Take here density Pm by RT. So here pressure is given 0.82 atmospheres. Next molecular mass of helium 4 we know. R value 0.082 into temperature 300. Therefore, we'll get value density 1.33 into 10 power minus 1 grams per liter. Therefore, option C. Grams per liter. Option C. Next. Rate of diffusion of H2 is 3 root 3 times that of a gas having formula Cn H2n minus 2. That is alkyne. So from this you can calculate n value by using Graham's law of diffusion. So first rate of diffusion of H2 by rate of diffusion of gas equal to root of molecular weight of gas by molecular weight of H2. So here molecular weight of gas 14N minus 2. So carbon 12, 12N plus hydrogen 1, 2N. 12N plus 2N, 14N minus 2 by 2, which is equal to 3 root 3 is given. Rate of diffusion of H2 is 3 root 3 times that of gas. So 14N minus 2 by 2 equal to squaring on both sides 27. So from this 14N minus 2 equal to 54 or 14N equal to 56. Therefore N equal to 4. N value 4. So therefore C4 H2N minus 2. C4 H6. Butane gas is given. C4 H6 butane alkyne. N value is 4. Next. Among the gases A, B, C, D, E, F, the gases show only positive deviation from ideal behavior. So only positive deviation means for positive deviation from ideal, Z must be greater than 1. So from graph clearly B and C can show only positive deviation from ideal behavior. B and C. Therefore option A. Compressibility factor 1 is given. 1 means ideal condition. Above 1, greater than 1. That is positive deviation. Below 1, negative deviation. Only BC are showing positive deviation. Only positive deviation. Next. Simple question only. A person living in Shimla observed that the cooking food without using pressure cooker takes more time. The reason at high altitude is at high altitude atmospheric pressure decreases. So therefore boiling point also decreases. Boiling point of water also decreases. So therefore food requires more time for cooking. Food requires longer time to cook. So option C. At high altitude Atmospheric pressure decreases, therefore boiling point decreases. It takes more time for cooking. Simple question only. Next. So among the following incorrect statements about real gases. So for real gases, we know Z not equal to 1. So that is Z greater than 1 or Z less than 1. Real conditions. Their compressibility factor never equal to unity, not equal to 1. So that is correct statement. Correct. The deviation from ideal behavior are less at low pressure and high pressures. Less at low pressure and high temperatures. That is also correct. At low pressure, compressibility factor Z equal to 1 minus A by VR. Next, third. Intermolecular forces are equal to 0. In case of ideal conditions, intermolecular forces will be 0. In case of real conditions, attractive forces will be present. Therefore, this one wrong. Next, they obey van der Waals equation PV equal to nRT. This is obviously wrong. Therefore, 3 and 4 are incorrect. Option D. So, here I will write at very low pressure and very high temperature, comma, PV will be equal to RT, which is ideal condition. For statement 2, we can write like this. At low pressure and high temperature, deviation will be very, very less. As the pressure increases, deviation will be more. Next. So, which of the following graphs correctly represents Boyle's law? So, already we have discussed about this. Boyle's law at constant temperature and number of moles, volume inversely proportional to pressure or PV equal to constant. This is very, very important. If pressure increases or volume increases, PV, product of P and V remains constant. Or we can write P1 V1 equal to P2 V2. Initial and final conditions. Remember these relations. So product of P and V constant, product of P and V constant irrespective of pressure and volume. So therefore, see options. With increase of pressure, if pressure increases, PV remains constant. If volume increases, PV remains constant. So this is observed in case of 2 and 3 graphs. Therefore option B. So if pressure increases, accordingly volume decreases, therefore P into V remains constant. If volume increases, pressure decreases, accordingly PV remains constant. So very, very important. Next. Assertion reason type question. Standard boiling point of liquid is slightly higher than normal boiling point. Reason. 1 bar is slightly less than 1 atmosphere. So standard boiling point 99.6 degrees centigrade. Normal boiling point, water is 100 degrees centigrade. So clearly, standard boiling point of water is slightly lower than that of normal. But here higher than normal is given. Therefore, assertion wrong. Reason. Relation between atmosphere and bar is 1.01325 bar. So based on this, assertion incorrect and reason is correct. Therefore, option D. Next. So 1 mole of oxygen gas at STP is equal to, at STP conditions, 1 mole of oxygen gas equal to 1 gram molecular weight of oxygen, and which contains 6.022 into 10 power 23 O2 molecules. This is standard condition. So clearly 1 mole of oxygen gas at STP is equal to 6.022 into 10 power 23, so which is Avogadro's number. Avogadro's number or Avogadro's constant, denoted with N0. So clearly option A. Avogadro's number of molecules but not atoms. And 1 mole of oxygen gas, 1 gram molecular weight. 1 gram molecular weight means 32 grams. Clearly option A. Next. So isocores are drawn at. So here remember these three terms: isotherms, isobars, isocores. So isotherms are graph between P and V at constant V, constant T. T and N also. N also constant. Number of moles also constant. Isobars, graph between V and T at constant P and N, number of moles. Isocore, graph between volume constant, here P and T at constant V and N. Remember these three. So isocores are at constant volume, graph between P and T. Therefore option A, volume constant. Next. If kinetic energy of O2 gas is 4 kilojoules per mole, RMS speed. So kinetic energy formula we know, 3 by 2 nRT, that is equal to 3 by 2 RT for 1 mole. For 1 mole of O2. Next, RMS speed. U RMS equal to root 3 RT by M. Therefore, in place of 3 by 2 RT, we can write in place of RT 3 by M into 2 KE by 3. Therefore, root 3 cancel 2 KE by M. So kinetic, and therefore URMS equal to root 2 into kinetic energy 4 kilojoules, that means 4 into 10 cube joules, by molecular weight of O2 32 grams, that is 32 into 10 power minus 3 kg. So from this we'll get value 5 into 10 square meters per second, or 5 into 10 power 4 centimeters per second. So therefore option C. Next one. At 27 degrees centigrade, 10 liters plus 4 grams of ideal gas mixture containing helium and neon. Helium molar mass 4, neon molar mass 20, has a pressure of 1.23 atmospheres. What is the mass percentage of neon? Mass percentage of neon. So here given, first temperature 27 means 300 kelvins. Next volume 10 liters flask. Next weight. So W1 of helium plus W2 of neon will be equal to 4 grams. Say this is expression 1. Next molar mass for helium 4, neon 20. Next pressure 1.23 atmospheres given. Next R value we know 0.0821 liter atmosphere mole inverse Kelvin inverse. Next we know that PV equal to nRT. So here we can write total number of moles. Total number of mole means N1 plus N2 RT. So which is equal to N1 means W1 by 4 for helium, W2 by 20 for neon into RT. So from this 25 W1 plus 5 W2 equal to 50, or 5 W1 plus WT equal to 10. Say this is expression 2. So from 1 and 2, we can write, that means simply solving 1 and 2. W1 is 1.5 and W2 is 2.5 grams. Therefore, mass percent of neon will be equal to, so neon mass 2.5 by total 4 into 100. So which will be equal to 62.5%. So option B, very very important. 1.5 grams of helium, 2.5 grams of neon are present. Mass percentage means mass of neon by total mass into 100. Next one. Here A, B, C, D, 4 different gases are given with critical temperatures. Which gas will be liquefied first? Very very important model. You no need to take A2, just A. A, B, C, D. So for A gas, critical temperature 304.1. For B gas, 154.3. For C, 405.5. For D gas, 126 kelvins. These are critical temperatures. So as the critical temperature means, I will write here, liquefaction of gas directly proportional to A, which is van der Waals constant, that is directly proportional to critical temperature. So simply, as the critical temperature increases, van der Waals constant A increases. We know van der Waals constant A is force of attraction. Force of attraction. As the critical temperature increases, force of attraction increases. As the force of attraction increases, liquefaction of gas increases. So here clearly C will be having more critical temperature. Therefore, it will be liquefied first. Important formula. Next. So which of the following is the wrong statement about the liquid? First statement, it has intermolecular force of attraction. So there will be force of attraction between layers of liquid. So which is correct statement? Force of attraction is present between two layers. Any two layers. Evaporation of liquid increases with decrease of surface area. So rate of evaporation directly proportional to surface area. As the surface area of liquid increases, rate of evaporation increases. But here wrong is given. Statement 3. It resembles a gas near critical temperature. That is also correct. Critical phenomenon. Next, it is an intermediate state between gas and solid. That is also correct. So incorrect statement is B. So rate of evaporation directly proportional to surface area. As the surface area increases, more number of molecules will be converted to vapor. Next. The volume of 2.8 grams of CO at 27 degrees centigrade and 0.81 atmosphere pressure is. This is also direct question. Here first take number of moles of CO. Given weight 2.8 by 28. So which is 0.1 mole. So next apply PV equal to nRT, that is P equal to 0.1 mole. So next apply PV equal to nRT, that is P equal to 0.1 mole. So next apply PV equal to nRT, that is P equal to nRT. So next apply PV equal to nRT, that is P equal to 0.1 mole. So next apply PV equal to nRT, that is P equal to 0.1 mole. So next apply PV equal to nRT, that is P equal to 0.1 mole. N naught T by V. So volume we should find. Therefore, I will write like this. V equal to N naught T by P. So N value 0.1 and R value 0.0821 into temperature 27 degrees centigrade 300 kelvins by pressure 0.821. So clearly volume will be 3 liters. So option A. So this is the end of the chapter. So these are important models of states of matter. In next video I will explain one more topic. Thank you.